Hello, this is question 14 on your November 2020 paper 1 from AQA. You have a function defined this way, and fx equals 0 has a single solution at the point x equals alpha. By considering a suitable change of sign so that the alpha lies between 0 and 1. So what we are going to check is the sign of f0 and f1, and if they are different, that means there is a solution or a root between them. So f0 is going to be 3 to the power of 0 times root 0 is 0 minus 1. So f of 0 is minus 1. And f of 1 is going to be 3 to the power of 1, which is 3. Root 1 is 1, so 3 minus 1 is 2. This one is negative, this one is positive, therefore there is a solution. There is a solution between 0 and 1. For the second part, we have to show that the derivative is this function here. So what we are going to do is to differentiate and see what happens. This is my function. So if I differentiate this bit, I can use the product rule. So I'm going to differentiate this, multiply by this, and then differentiate this, multiply by this. Yeah. So derivative of 3 to the power of x is 3 to the power of x ln 3. Then I'm going to multiply that by the second one, so root x, the second one, plus the derivative of this one times 3 to the power of x. So plus 3 to the power of x multiplied by the derivative of root x. Remember, root x is x to the power of 1/2. So if we derivate that, we have 1/2 x to the power of minus 1/2. And then this second part, the minus 1, that's derivative is 0. So now we have to make this looking like this one. So we have a bracket, and outside we have 3 to the power of x. So we can start doing that because we have 3 to the power of x in both sides. So I can write that 3 to the power of x and then a bracket. Here I have ln 3 root x, or root x ln 3. Then I can put this in the denominator as 1 divided by root x. So plus 1 divided by 2 root x. Just because I have a root x in the denominator and it's going to come from here. And now I'm going to add these two functions. So I have those two terms. So I have 3 to the power of x and 2 root x times root x ln 3. I have 2, and root x times root x is x, and ln 3 plus 1 and all divided by 2 root x. I'm just adding these two terms. And now I'm very, very close because I have this one here, the 2 root x, and this x ln 9 comes from bringing these two to the exponent. Yeah, so remember, when I have a ln b is going to be ln b to the power of a. Yeah, so I'm putting that 2 as an exponent for the 3, and then I have the expression. So I have 3 to the power of x. I can write the 1, I can swap the terms of x ln 3 squared, which is 9, and all divided by 2 root x. So that's my derivative. And now is when I have to apply numerical method. So use the Newton-Raphson method with x1 equals 1 to find x3. And we have to give the answer to 5 decimal places. So if you go to your formula booklet, you have the Newton-Raphson iteration is the formula, is this formula here. So you just have to apply it. We have that x2 is going to be x1 minus fx1. I'm just writing the formula for x2. Yeah, x1 is 1. F of x1 is f1 that we already found it. So f1 was 2. So I can use that because I already know it's 2. Then divided by f prime of 1. f prime was this function here, so I'm just going to substitute by 1. So I have 3 to the power of 1, so divided by 3, 1 plus 1 ln 9, so ln 9, divided by 2 root x, and x is 1, so 2, because root 1 is 1. You put this in the calculator, and the answer is 0.42, no, wait, 0.582971, and so on. What you're going to do is to not lose decimals. You're going to put this value in the memory of the calculator, because I think it's too complicated if you try to use the ANS button. So you put this in the calculator in the memory, and then we find x3. x3 is going to be x2 minus f of x2 divided by f prime of x2. And I'm going to write just 0.58, but what you have to do is to bring your memory out. Yeah, so if you put this in memory A, for example, what you're going to do is using A all the time. So x2 is going to be your value in the memory minus fx2. The function, remember, is this one, so I'm going to write the value here, so it's going to be 3 to the power of the value in the memory of the calculator, root memory minus 1, and then in the denominator 3 to the power of the value in the calculator, 1 plus the value in the calculator again, ln 9 divided by 2 root the value in the calculator. Yeah, I'm writing only 0.58, but you should be using the value that you have in the memory, yeah, of the calculator. So you put this in the calculator, and you get 0.424653. Those are the first few decimals, and we have to run to 5 significant 5 decimal places. So I have 0.42565 to 5 decimal places. And then the next part, I have to explain why the Newton-Raphson method fails to find alpha when x1 is 0. When x1 is 0, our function derivative is not defined, because I have root 0, which is 0, so my denominator is 0. So f prime, the derivative, is not defined. So for f prime 0 is not defined. The fact that the derivative has 0 in the denominator just means that the tangent, the gradient of the tangent, is infinite, or the tangent is vertical. Yeah, so you can clarify that, but not necessarily. So it's enough if you say that the f prime is not defined, because then you cannot apply the method. So tangent is vertical. Yeah, and that's all. That's everything that you have with this question.